Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about types of furnace. So let's dive deep into it. Now, first you have to understand furnace is a big broad category, so let's quantify it. It's basically an ancient hot box, and yes, we have been making it for give or take 5,000 years. So it is a very critical component of every civilization. And what does it meant to do? Basically, it's supposed to get hot and it's supposed to stay hot, as in it should be able to handle its design temperature like it's not a thing, meaning it should not care, oh, you are melting metal. It's like it should not care. It's like, bro, I got this. They're like, okay, it's 700 degrees Celsius for 30 days. I should not care. That's the whole intent of it. And temperature can range from a very mild 100 to 200 degrees Celsius to stupid 3500 degrees Celsius. So you have to understand this is a very dynamic subject. Like, people will spend their whole life and they will only be able to master one slice of this range, so to say. And it's used for everything from food to metals. And it's what we classify as root technology. For example, right now everybody is like hyping about, oh, we want semiconductor history. How the heck do you think that starts? Tada! Furnace. And again, it is not as simple as you might think, oh, you put some material and you just melt it. Nah, it has to be done in a properly controlled environment. For example, you cannot have oxygen there. Most likely you would require either to pull vacuum or argon purge it. So that has to be done. And not to mention, you have to spin a molten material, which is at very high temperature. And then you have to slowly pull something out of it. Yeah. So let that be very clear. Many times furnace technology does not get that much attention, but the reason for that is it's assumed that it is sorted, but it's not. It's like it takes engineering. Let that be very clear. A good furnace in a country equals good yield. Bad furnace yields high cost of living. That's how important furnace is. So let that be very clear. This is root technology. Many technology tree starts from it. They assume you have a good furnace. If you do not, yeah, lol. So temperature are generally classified in certain range categories. For example, different temperature for different tasks. Duh. So you are dealing with bakeries, food, or PCBs. They are generally dealing with 200 to 300 degrees Celsius. So the PCB reflow ovens generally do not need to go very high. So that's the temperature point of view. Then you have ceramic and glass kiln. We have a lot of experience with this. They generally target 1000 degree to 1300 degrees Celsius. So now we are getting some serious temperature. And metal, heat treating, let that be clear, not melting it, but heat treating it, that requires certain spicy puppies, as in 1200 to 1600 degrees Celsius. So yeah, now you are pushing the kiln, so to say. And then you have like still making itself, yeah, that is above 1600 to 2000 degrees Celsius. So, oh, and many times you will like, okay, if steel melts at like this temperature, why does the furnace have to be so hot? It's energy flow. If you do not have high enough delta between your source, as in like whatever it's creating that heat, and whatever you want to melt, it will take too goddamn long. It will be too wasteful. That's why your soldering iron, even though solder itself can easily melt at 250 degrees Celsius, your soldering iron can easily go 300 or even 450 degrees Celsius. That's by design. Same way, furnace, even though it does not need to be that high, but it will take freaking forever to reach equilibrium, that temperature. But if you have high flow rate, as in like the T delta is huge, whew. So that's why the temperatures are generally much higher than they have to be, bare minimum. And then you have the categories we do not talk about, we call ultra high temperatures. Basically, these puppies cross 3000 degrees Celsius. It's like it requires a zirconium level material in order to handle it. Because again, at 3000 degrees Celsius, most materials just like give up. It's like, bro, I can't deal with this. Even alumina oxides are like, no. So yeah, that's a complex thing. So let's dive deeper into the working aspect of it. Well, generally we deal with electricity. That's the benefit of modern technology. And we have electric resistive heating. That's the step one. And generally you can do surprisingly a lot. But let that be very clear. If your nichrome wire or some sort of element itself is only going to 1600 degrees Celsius, meaning your kiln or box or oven must be below that. It will always be below that. So it does not go very high temperature. Although if you are dealing with aluminum, it's like, bro, we got this. We got this. We good. We got this. You're dealing with like, you know, pottery and all that, you got this. So, but steel melting and all that, ooh. So, although now we do have some carbide material, certain specific type of it that can almost push 1650 degrees Celsius, You can do that, but again, generally if you are below 1200 degrees Celsius, electric resistive heating is like best. Then you have electric arc furnace. Temperature becomes pointless at this point in time because you are literally creating a short circuit and that's creating electrical arc. Temperature be damned. It's just what material is there, what is the ambient environment. Temperature is be damned. You control the temperature. So electric arc furnace is the backbone of modern industry. Like you see those three phase of prongs going in and go. Yeah, that's the arc furnace. And temperature is just, it's plasma temperature. It's literally creating plasma arc. So you don't have to worry about it. Then you have electric inductive heating. Now this puppy requires selective material because while arc can work with almost everything and resisting will work with everything, inductive does require a certain material choice. I mean, like it will not work with ceramic. But if it does work, it does allow you certain benefit. For example, your heating material is heating element is no longer consumed. In arc furnace, those rods are consumed, not in day one, but they do get consumed. Here you don't have to worry about it. Heck, even the insulation becomes better. You can, because you are coupling the energy through magnetic flux rather than like having a drilled through or pouring or something like that. So electric inductive is really good, but it does have certain choice. It's a very finicky kind of system where it's like, hey, this metal alloy, me good. This material I will not touch. So you have to be mindful of that. Then we have plasma arc in a vacuum. Wait a minute, how can you have plasma in vacuum? Well, you generally pull out a vacuum, have your material, and have a high, almost like an ion engine going whoosh. So that's how you get your plasma in ultra high temperature. Of course, there are certain inert environment plasma torches also, but they go to very high temperature, like thousands of degrees. Basically, you can melt ceramics at that sort of temperature. Then you have combustion based system. Basically, you must have seen like people using propane. Coal furnaces are also a very critical technology because coal power plant do not just like take water and heat it up to 100 degrees Celsius. The fire in coal furnaces can easily be 1600 degrees Celsius. And like, okay, why? Well, here's the deal. For steam to reach what we call supersaturated steam and be useful, it has to have very high T delta. How high T delta? Generally, we are talking about steam that is going in the turbine. Generally, it is at 1000 degrees Celsius. It is hot, and again, you can't achieve 1000 degrees Celsius steam if your fire is not that hot. So fire has to be hotter. So combustion based systems also exist, and again, you can understand that we are talking about hundreds of degrees Celsius, 1000 degrees Celsius, 2000 degrees Celsius. It does require effort. It's not just like tada. And again, if you can do it well, you can insulate it well, you can design it and maintain it well, it directly affects into coal consumption for energy production, fuel consumption for water heating, all again district heating and all that. So in those sort of scenario, directly affects the quality of life of your civilization and basically inflation, so to say. So it is one of those things where people have to spend their whole life just to gain 1% extra efficiency, and it matters. Then we come to the environment aspect of it. High temperature environment is very reactive, meaning you can have stuff and it does not care. But you have that same stuff and in elongate it to 1000 degrees Celsius, it might start creating horrific reactions. So that's the whole point. Like if you have like, you know, PET tubes and 3D printing parts, in normal temperature, who cares? But heat it up to 300, now it has like harmful toxins emission. So that's why high temperature is very reactive with everything. Everything starts to react at high enough temperature. So if you have a thing that does not care, for example, food, ceramics, pottery and things of that nature, just use air. That time you do not have to worry about it. But if you are dealing with something that is sensitive, but you can live with it, you generally use nitrogen purging in order to reduce the oxidation. Let that be, nitrogen will react. A high enough temperature, it will react. But again, that may be very little of an issue or may not matter at all. So nitrogen is generally not that peak, but it's like better than just having oxygen. So nitrogen is there. It reduces oxidation, does not eliminate it. Then you have argon, where you are dealing with very reactive material like magnesium or something like that. At that point in time, you do have to give a damn. Argon is there. And then you have vacuum for ultra pure stuff, basically silicon ingot, vacuum. But again, let that be clear, vacuum can also be used for some other means, so to say. It can also be used as a temperature control. Like, wait, what? Well, the most advanced, complicated black magic technology is single crystal turbine blades. Now, how do you make it? Well, you have a molten form, and it's molten metal of super alloys. Cool, awesome, GG. Now you have to pull it down, cool the bottom part, and keep the molten layer line very controlled, as in like where that liquid to solidification is happening, that has to be controlled. Now here's the deal, you can't control it if you have gas, because the moment you pull it out of the oven, let's say the base part, you are running liquid cooling through it. Cool, awesome, you're cooling it. But if there is air here, air will try to equalize the temperature. Top could be like, let's say 1300 degrees Celsius. Not 2000 degrees Celsius. It will try to equilibrium it to the bottom part. So you pull vacuum here, and then the heating elements dump energy via photons. So pulling it out allows you to control it very well. Meaning the line, basically where the solidification is happening and where it's still liquid, it can be stopped. That's why vacuum is used to control temperature many times. Of course, for purity and silicon industry and all that, that's like duh. But in other scenarios, it's also very desirable, so to say. So temperature control and certain key things require this sort of attention and care, where you have, like, you know, element of control. For example, powder metallurgy, you made powder parts and you are sintering it, but if you have oxygen, because powder metal is powder, it has bonkers surface area. If oxygen gets into it, the end, your part would be like kaput. You have to basically put a nitrogen or carbon. You may want to infuse carbon on the surface, so it becomes very hard. It has softness of the core in the back end, and it becomes hard on the surface, almost like katana. Katana is like very well known because it's a bimetallic blade. Now, like, okay, wait, it's made out of one thing. They temper it differently. So if you look at the edge part, it's very shiny, very hard, so they edge it. But you look at the back wavy pattern, basically when they are forging it, tempering it, they put clay and then they put in a furnace. So the back end does not get hardened. Now, why? Well, if you need a very high hardness in order to maintain the edge, the sharpness. Cool, awesome. But if you made the whole blade hard, the moment you strike two hard metals, kaput, it will shatter like glass. So to make sure, it's basically hardness is used to handle the edge, softness is utilized to handle the shocks of it. So that's how you get the two metallic system. Same thing is done in almost all modern metallurgy system, where it's like, okay, which place requires the hardness? For example, gear teeth, you want the teeth itself to be hard, but the core, so it does not shear or shatter, to be soft, but the wear surfaces to be as hard as possible. So all of these things require control of the environment, not just a black and white thing, control of that environment. Now we come to the actual control aspect of it. Furnace is not a dumb device. It's not like on equal hot. It's not a dumb device. You must have seen all the furnace, and they have that, like, you know, giant, a big black box. That's a PID controller. So because it's a fine-tuned system. What does that mean? Well, every material you are dealing with, generally, including food, has its own temperature profile, meaning how you ramp it up, how you soak it, how you stabilize it, and then how you cool it down, and then how you rapidly you reach equilibrium. All of these things are controlled, and if you fail to comply, for example, let's say you are doing soldering and you do not follow the manufacturer system, your basically soldering output is random now, meaning you could have a perfect connection or you could have a random connection, and you will never be able to figure out what the hell happened. So this does require you to follow the intent very precisely. Failure to comply simply means your batch goes kaput. You could have a metal that looks fine, but it has so much internal stress, the moment somebody puts load on it, kaput. So that's a very serious thing that you have to understand. How quickly you ramp it up, how quickly you ramp it down. Cooling is also very important, because again, there are two vectors that are going against each other. You want something that is like retains the heat, very awesome, so you require less energy to heat it up. Cool, awesome. But how you gonna cool it down? For example, this is a soldering paste temperature. So you ramp it up slowly. You ramp it up 2 or 3 degrees per second. Slowly ramp it up, so you do not create shock. You do not have parts bouncing off and PCB warping. So slow ramp up, and again, that's why the temperature rise speed is so slow. And then you keep it there for 60 to 120 seconds. So everything becomes equilibrium. Then you go YOLO on it, you go yoing. Then you go to 4 degrees Celsius for like a 60 to 90 seconds, and then your peak temperature crosses to 260 degrees Celsius, then you drop it. Now dropping you have to do at minus 3 degree per second. You have to cool down fast, and that's why whenever you see the PCB ovens, they generally have different segments, because again, the engineer will design a heating section that's like, I can give you 4 degree second very quickly without causing too much electrical wastage. But it's like, if they do that, like insulated, design it properly, it will not cool down fast enough. So what do? You heat it up, move the board into different sections. That section would be like for cooling. It will be designed for cooling specifically. So you can control that minus 3 degrees per second drop effectively. And by the way, that can also be done for metals, but most of the time metals are not in a scenario where they need rapid cooling unless you're dealing with some certain alloys, certain ceramics, certain grain structure. Most of the time you do not have to worry about it. And if you're dealing with ceramic pottery or insulators or things of that nature, you also have to worry about density increase, density, peak density, and like, you know, density decrease. You're like, yeah, you would think temperature keeps going up, na? It reach a point where it will backfire on you. Oh, and not to mention structure might have fell, like you might have like a shape and it's like, bleh. So all of these things have to be mattered. So this graph has to be controlled: ramp up, hold, soak, dwell, then cool down, all of those things. And you will hear units. For metal, we generally talk about like, you know, 10 degrees per minute, and cooling would be minus 5 degrees Celsius per minute. So if you made like a super duper epic perfect insulator, yeah, you can't do much with it. You might require like a pipe which is inside there, ceramic pipe, and you completely close it. But when you need to cool down, you open the taps and you blow air through it, so it drops the temperature reliably. So it is a very, what you call, fine-tuned craft. It's not just duh. It's a very fine-tuned stuff. And that's why, like, it's root of many technologies. If you do not have a good control over furnace, especially advanced materials, forget about it. Like, just forget about it. Don't even waste your time on it. It's just, you need quality furnace technology. Without it, nothing matters. So this was my presentation on basically furnace technology and types of it. Hopefully you have liked it, learned from it. In that case, please hit the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show my extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.